In this experiment, both the techniques of solid to liquid and liquid to liquid extractions were used to isolate caffeine from tea leaves. Sublimation was also used as well as the final purification technique. Before conducting this experiment, there are some key things you'd want to know about the chemicals involved in this experiment. As far as safety and disposal for sodium carbonate, as you can see here, for sodium carbonate, you do not want to ingest or breathe. You always want to wear protective, suitable clothing, and you want to keep it away from acids. You also, most importantly, want to avoid contact with your skin or eyes when dealing with sodium carbonate. And as far as disposal goes for sodium carbonate, you want to dispose of it in the non-halogenated waste container. For caffeine, as you can see here, it can be hazardous in situations of skin contact, eye contact, and you do not want to ingest or inhale caffeine. As far as disposal goes for caffeine, you want to dispose of it down the sink. For the safety on methylene chloride, as you can see here, you want to know that it is very hazardous in case of eye or skin contact, and you always want to avoid situations of ingestion or inhalation of methylene chloride. As far as the disposal goes for methylene chloride, you want to be sure to dispose of it in the halogenated container since it contains chlorine, which is a halogen. Last but not least, when dealing with sodium sulfate, you want to know not to breathe or inhale or ingest the chemical, and you always want to avoid skin or eye contact with this chemical. As far as the disposal goes for sodium sulfate, you want to dispose of it in the non-halogenated container. For this experiment, these are the apparatuses we used to obtain the desired product that we wanted. First off, we used this apparatus in order to do a solid to liquid extraction. The tea leaves are the solid, and within the tea leaves are the caffeine. The caffeine is soluble in water, but is more soluble in hot water. So by heating the water with the tea leaves, the caffeine is broken off from the solid component, the tea leaves, and is in the aqueous layer. To ensure that minimum water is lost, there is a water-jacketed condenser that allows the water to boil and heat up so that the caffeine is broken off from the solid and remains in the aqueous layer, but at the same time allows for minimal water to be lost since the vapors will condense and flow back into the mixture. Also, to prevent water loss, we replenish the mixture with water when necessary. We also added sodium carbonate to this mixture. The sodium carbonate acts to deprotonate the water so that the water doesn't become acidic, because if the water does become acidic, it will react with the caffeine, and we do not want the caffeine to react. Right here we have the water-jacketed condenser. The round bottom flask is right here. Water will go in through here and it'll go out through there. And last but not least, our heat source is right here, which is the heating mantle. Once we got our aqueous layer that has caffeine in it and the solid, which are the tea leaves, we used a vacuum filtration to filter out all the solid, isolating the aqueous layer that contained the caffeine and other impurities. Next, we used a liquid to liquid extraction. We used, in this liquid to liquid extraction, methylene chloride. We did this because caffeine is more soluble in methylene chloride than it is in water, so thus it would be more attracted to the methylene chloride than it would to the water, thus extracting out more caffeine along with the methylene chloride. As you can see, this is the aqueous layer, and this is the organic layer, the clear layer. Once we got all our methylene chloride with the crude caffeine in it, we heated the extracts, since caffeine has a much higher boiling point than that of methylene chloride. The methylene chloride would evaporate, leaving behind the crude caffeine crystals, as you can see here. To purify the crude caffeine, we used sublimation. Three components were necessary in order for this to be purified: high temperature from the outside, low pressure, and on the inside, low temperature on the tube. The tube here, as you can see, has ice. The high temperature would evaporate the caffeine, leaving the impurities behind, and the caffeine vapors would recrystallize on the tube with the cold temperature. Once that occurred, we ran our crystals through a melting temperature apparatus to compare the melting point of our crystals to the literature value in order to determine whether we used proper technique or not. As you can see, this is the melting temperature apparatus, and inside we have the capillary tube with the crystals. For the students' results from a measure of 1.55 grams of tea leaves, the student yielded 0.0121 grams of crude caffeine and 0.0038 grams of purified caffeine. For the melting point of the purified caffeine, the initial melting point of the student sample was 190 degrees Celsius, and the final melting point was 235 degrees Celsius. As far as the calculation go, for the mass of crude caffeine and 1 gram of tea leaves, the student calculated it as follows. For the mass of crude caffeine, he had 0.0121 grams all over the mass of the tea leaves, which was 1.55 grams. The student, for the mass of crude caffeine and 1 gram of tea leaves, yielded a number of 0.0078. For the percent recovery for the sublimation process, the student calculated as follows. He took the mass of purified caffeine, which was 0.0038 grams, all over the mass of the tea leaves, which was 1.55 grams. He took this quotient, multiplied by 100 to get a percent recovery of 0.245%. For the melting point of pure caffeine percentage error, the student calculated as follows. He took the experimental melting point subtracted by the literature value melting point in an absolute value, all over the literature melting point, multiplied by 100. So the experimental melting point he had was 235, and the literature melting point was 238, all over the literature melting point, which was also 238, multiplied by 100. And the number he received for the percent error was 1.26%. Here we have an H&MR spectra. An H&MR spectra helps us determine a molecule by allowing us to observe the different protons or different hydrogens per se within a molecule. By seeing the different protons presented to us through the chemical shifts, we can come up with a molecule. The chemical shifts tell us the type of hydrogen, and the integration of each signal tells us how many equivalent hydrogen are on each type of hydrogen. The multiplicity that we get from each hydrogen, which in this case from A to D, they're all singlets, shows us how many neighboring hydrogen there are to each alpha hydrogen observed. Since each one of these are singlets, it tells us that each alpha hydrogen observed has no neighboring hydrogens. As far as the D-shielding goes, A is the least D-shielded and D is the most D-shielded. Least D-shielded meaning that it has the smallest down field, meaning that it is the most shielded per se. And D meaning that it is the most D-shielded, meaning that it has the largest down field, which also means that it is the least shielded proton. But with the H-NMR spectra alone, we cannot get the full structure of the molecule. For example, we may not know that the molecule might have pi bonds or rings. So, with the help of IHD, we are able to determine how many pi bonds or rings a molecule has through its chemical formula. So specifically for caffeine, the chemical formula is C8H10N4O2. So for the IHD calculation, we take 2 multiplied by the number of carbon, which is 8, plus 2, all in parentheses, minus 10 hydrogens, plus the number of nitrogens, which is 4. We ignore the oxygens when calculating IHD, and if halogens were present, we would take that into account, but caffeine does not contain any halogens, so we do not have to take that into account. So we take this whole number right here, divided by 2. That gives us a number of 6, which makes sense, since the IHD gives us the number of pi bonds and rings. Since it gives us 6, as we can see here in the molecule, we have 1 pi bond, 2 pi bond, 3 pi bond, 4 pi bond, 1 ring, which 4 plus 1 is 5, and another one, which is 5 plus 1 is 6. So to conclude on that note, the IHD helps us remarkably when determining the structure of a molecule, alongside with the H&MR spectra.